Thank you very much, Max. It's a great pleasure to be here with you guys. So I want to thank both of you, both Max and Jeremy, for the invitation to talk to you guys. And I think it's a very exciting sort of workshop, because it actually, as I was talking to Jeremy before, it actually mixes kind of Hasklers and Agders and kind of real functional programmers with more mathematically minded people. And of course, I actually feel better on the more mathematically minded people. And so I think you should think of this keynote as being a little bit of a meta talk over the talks of today. So today I want to talk to you about two papers that are kind of old work of mine, and that actually I think are still very important, and I wanted to kind of try to drum up support for these ideas. So these two papers are listed there: the categorical models for linear intuitionistic type theory, and the relating categorical semantics for intuitionistic linear logic. And this is kind of seems fairly topical nowadays, but we could start from old history, because it's always good to know where you're coming from. So the reason why I liked so much linear type theories is, as Max was saying, because I have actually done quite a bit of work on that. And this work starts from Gödel's dialectic interpretation, which I did under Martin Hyland's supervision a while back in Cambridge. And when I was working on that, I realized that the internal categorical model for the dialectical interpretation corresponds to linear logic, intuitionistic linear logic to be precise, not to intuitionistic logic, which is what everyone expected it to be. And these are kind of, this is just a kind of a funny joke, well, at least for me funny, the fact that these are my ancestors in terms of Martin was supervised by Robin Gandy, the second person on the pictures, and Robin Gandy was the only student of Alan Turing. So kind of I can count Alan as my great-grandfather, kind of academic great-grandfather. And when we discovered this business that the dialectica did not have as its internal logic, intuitionistic logic, but actually some version of linear logic, Martin, Nick Benton, and Gavin Bierman, and myself, we kind of started thinking hard about linear type theories. And we came up with the first linear type theory that one could prove correct. And then Gavin wrote his PhD thesis on that. And then Nick worked on his own version, the NL calculus, which is kind of nowadays the one mostly considered by people. Gavin is nowadays with Oracle doing Java, and Nick is with Facebook doing Hack. So kind of, so they were the real functional programmers on this initial work. And at that same stage, Andrew Barber, who was a Gordon Plotkin student, came up with what I thought was the best formulation for a linear type theory, which is the DILL calculus. The DILL stands for dual intuitionistic and linear logic. And I just said the best formulation of a linear type theory. And I guess I should explain why best formulation and which kind of criteria I was using for this, for using best here. And I was actually thinking about the projects that we had in Birmingham many years ago, this project called Explicit Substitutions Linear Abstract Machines. And this was kind of very important for me, and my only kind of real claim to be actually talking in a functional programmer sort of conference, because at that stage I was kind of a big proponent of linear functional programming, and actually I think I still am that many years later. And the reason I thought this idea of linear functional programming was so cool and clever was this fact that we had at that stage quite a bit of work on categorical combinators, which is an idea originally due to Pierre-Louis Goudian. And as I was saying, Eike Ritter, who is the person that I kind of mentioned at the beginning, but that I wrote the name at the beginning, but didn't mention so much, he had finished a PhD thesis in Cambridge on categorical combinators for the calculus of constructions. And I had just finished, as I was just mentioning, a PhD thesis on models of linear logic and linear type theories with the guys. So we put the two together and kind of thought about having categorical abstract machines for linear functional programming. And that was our project. Because I have been resurrecting this long forgotten project, and I presented some of this work in Cambridge recently, Martin came up with this turn of phrase that I think it's fairly interesting. So he calls it categorical structured syntax. This idea that you have your category theory informing and guiding and giving suggestions for what sorts of syntax you should have in your functional programming. And it's a great pleasure to, after those many years, kind of being in a place like the Topos Institute, which I hope all of you have heard about. And if you haven't, please go and just type Topos Institute in Google and check us out, because we have a very different model of things to show you guys. So what happens kind of more than 20 years later? We had loads and loads of papers submitted to conferences and some not even submitted. We had only 2 journal papers, linear explicit substitutions and relating categorical semantics, the one that I actually want to remind you of. We had someone who did a master's thesis and a kind of proof of concept implementation, Francisco Alberti, who then went to do a PhD with Pierre-Louis in Paris. And we had several international workshops on, 3 of them I mentioned there, on these ideas of functional programming with a very strong mathematical basis, which is kind of very nice to see in MSFP. I think it's the same basic idea that we had kind of then, but much bigger as you have it now. Very good. So I wanted to kind of get, now that I'm in the Topos Institute, not having to think about 3 months improvements to the bottom line, I kind of want, so you probably kind of missed some of the bits, but I actually came to Silicon Valley kind of 20 years ago, a bit more than 20 years ago. And then I had to abandon all this interesting work on linear functional programming because Silicon Valley has a very different sort of goals and objectives. And, as I was saying, every 3 months, you have to provide something that either improves the bottom line, or you can convince someone else that it will in the next 3 months. So the horizon of research can be quite a bit narrower than what one has in Europe by and large. And so I had all this kind of interesting work and papers that had not gone anywhere. And I'm now trying to get them all up and updated and done properly. But I also have to confess that by that stage, I had these two little ones down there, and the xSLAM project, as far as I'm concerned, it was a total success, because it had more than 15 publications and stuff in 3 years or 4 years because of changes, and so it was a success of under certain considerations. Now, many years later, we have a situation that looks rosy again, because first we had this idea that Rust, this idea of actually kind of promoted by Alan Jeffrey, that that Rust kind of is doing what we were doing kind of in 1992, using kind of proving the linear type system sound and complete and actually more than that. So that was happening according to Alan in Rust. And even more recently, kind of in 2018, we had this thing about linear types, adding linear types to Haskell. And nowadays Haskell does have, let me see, we had this before, Jeremy, let's see if we can stop the thumbnails from appearing. Just a second, guys. I will exit the full screen and come back. As it goes back to the beginning. That's not so good. Sorry about that. So as I was saying, we had this in 2018. We had the Haskell committee kind of mentioning that they would really that they had been, the proposal for linear types had been accepted. And just now, kind of just last year in ICFP, we had 2 talks, one on why functional programming with linear types by Maietti Bosflug, and one on linear Haskell today and tomorrow by Jean-Philippe Bernardi, and you know that the preprint about linear Haskell is has been in the archive for a while. So I think maybe it really is time to kind of bring back these ideas of what happens in linear Haskell as far as a more mathematical person is concerned. So I think I don't need to belabor this point that that the kind of stuff that I do, and I hope most of you do too, is categorical proof theory. So we actually want to model derivations and proofs, not only whether terms are true or not. We want to think of proofs as definitely first-class citizens. We want to use an extended version of Curry-Howard that actually pays attention to the categorical models. And we think that this is good because modeling derivations is useful when you're actually thinking about the proofs. You need to think about the proofs themselves in linguistics and functional programming and kind of optimizing compilers and lots of other situations. And the thing that is problematic about this whole idea is the fact that we have very different tools in different sides of this attempted merge of communities. So the reason this slide is here is because the last time I gave this talk in 2019, when I was working for Samsung Research America, I was actually talking to logicians. I was talking to proof theorists in a meeting for proof theoretic semantics in Tübingen. And then I was trying to convince the logicians that they should pay attention to what functional programmers have to offer them. And kind of today, I'm actually trying to do the opposite. I want to try to convince functional programmers that they should pay attention to what the logicians have to say, because this widespread use of logic and algebra means that we can solve the problems in whichever side of these frameworks is better for us. So, you know, if you're kind of wanting to calculate with category theory, you can, and then you just translate it to the functional programming thing, and vice versa. If you kind of come up with a cool idea in the functional programming, you might, with a bit of luck, be able to translate it back and produce some sort of neat categorical construction. And we've seen some of those earlier today. So, so I wanted to start, I mean, now, I don't want to be very offensive to people, but it is the case that that functional programmers can produce lots of syntax without lots of semantics to back them up. So I don't, I want to talk, I mean, so what I mean by that is that there's lots of other kinds of linear type theories around, but I wanted to discuss with you the ones that I know about the categorical models, and they have been proved sound and complete. And these are these three ones. They're the original linear lambda calculus that they're the work with Martin, Benton, and Gavin. This DILL system that was Plotkin and Barber in 1996, and an NLL system that lots of people use nowadays. Now, what's the difference between these three type theories that have models? Well, the difference, the initial one, kind of people, it's traditional lambda calculus. So you have traditional lambda calculus with a linear function space. So you have to be paying attention to where things are used and how many times they are used or not. And that means that you end up with loads of commuting conversions, both for explaining your tensor and especially where things were kind of very wrong before, when you actually have your Schreck operator. Because the point of linear logic is not just that you actually can pay attention to where things are used and where and how they are consumed, but the fact that you actually can have your cake and eat it. You can have this accounting for resources, and at the same time, you can forget the accounting for resources if you so wish. So you want to go back to normal functional programming, like in, I don't know, Thunder ML or something like that, forgetting the effects, then you can. And so that the problem with this system that was traditionally called the linear lambda calculus is that it's not very good for implementations. It can be seen as directly coming up of the intuitions of the logic, but it's not good. It's a kind of, as I was saying, two verbose, too full of commuting conversions that are a pain in the neck. The system that Barber came up with kind of tried to make good on Abramsky's original idea and kind of corrected the promotion rule in a ways, in a kind of interesting way, because you create this notion of a dual context, a context that separates assumptions that are linear from assumptions that are intuitionistic. And then you still have to deal with some of the commuting conversions, but at least the rule that introduces this the Schreck or bang becomes a cleaner rule, and you can try to, you're aiming to keep the old implementations of intuitionistic logic together with this new, with this ability to talk about things where you pay attention to the resources. And as I was saying, the third...
Sorry, Valeria, I have a question.
Sorry, I couldn't hear. Can it... Who's saying? And I can't hear my...
Max has a question in the room, I think, but
Good. What is it? Did you hear, Jeremy? I couldn't hear.
No, there's feedback on the microphone, so if Max knows the question, Max could type it and I could read it.
It might work if Valeria mutes and Max unmutes at the same time. I don't know.
Yes.
I can't. I'm having a. I mean, I think for muting myself, I need to stop sharing.
Can you hear me?
I can mute you, Valeria.
Okay, wait. Can you hear me now?
Yeah.
Yeah.
Okay. Can you go back one slide?
Sure.
Why in this bottom left rule, the introduction rule for the bang? Why is it a gamma semicolon underscore? Why isn't it nothing on the top and an arbitrary delta on the bottom?
This might be a typo, because I think you can add the deltas. You can add things that are not. No, you can't, right? You know, it's got to be an empty thing, because every to add a pling, to add a bang to a term, you have to have used only things that were plinged or banged to begin with, right? The whole point of having intuitionistic formulae is exactly that there were no linear things used to produce it, because if there had been linear things, then you could cut into those. So the difficulty that existed before, that caused the linear type system that I showed earlier on to be necessary, was that to use Phil Wadler's phrase, there was no substitute for linear logic, which was a very clever wordplay on Phil's part, because it looks like he was saying that linear logic was the best thing ever, but actually what he was saying was that there was a problem with substitution in the linear lambda calculus that, say, for instance, Abramsky had produced. So the point here is that you need and it's the same rule that you have for any modality whatsoever. So that this problem kind of carries on for all the newer modalities that people want you to think of. You cannot have anything that is non-modal kind of, if you want to put a model here.
So I think actually the one that was confusing was the graph one, not this one. Why does that one have an empty context below but an arbitrary delta up top?
The introduction, sorry, which one?
That one, yes. Like where did the delta come from?
Well, I'm sorry.
I don't
remember what that one was about. So,
okay, thank you.
You know, we can try to talk more later, but okay. So I was saying that the point about the NLL system is that it is very clever as a piece of semantics, and now I'm going to kind of in the next slide talk about the semantics. But in terms of syntax, it is it's a compromise that is not so cool, because it's kind of making type theory out of category theory. So you do have directly your adjunction sitting here. So you have your G of A and your F of A. There's my F. My F here, F of X, and your G of A. So you just kind of take your adjunction and rewrite it as if it was type theory. And you might say, and why don't you like it, Valeria? And I don't like it because I think, if it is to be a modal type theory, we should try to follow what the modal logicians have been doing before, instead of kind of trying to convince them that adjunctions are the best thing under the sun. But in terms of, our business is actually, it's not to do syntax only or semantics only. Our business is to do both of them at the same time. And the categorical models that we have kind of try to do that, try to kind of be both syntax and semantics. And the categorical models are kind of, I just kind of repeating what they are here. So the linear lambda calculus had the first model, and it's a linear category. So, is simply a symmetric monodal closed category equipped with a linear monodal comonad. Linear comonad, I think, is another Martin Hyland way of packaging information in a single phrase. And such that the co-Kleisli category of the comonad is the Cartesian closed category. So the point is that you're transforming your logical intuition that you have linear types and normal types, and that they actually live together in such ways as, whenever you put a pling or bang on a linear type, it becomes an intuitionistic type. You're making this intuition into category theory by using a co-Kleisli category. And this kind of description can be simplified by saying, in the case of the DILL system, can be simplified by saying that there is a monoidal closed adjunction between a symmetric monoidal closed category and a Cartesian category. And as I was saying, you can even go further and simply say, well, okay, now, you guys should do that type theory as if it was category theory. So go for an NLL system, because that is simply the only thing you need is a symmetric monoidal adjunction between an SMCC and a CCC. And this is much easier to say and to describe. I can make little pictures like that. You have a Cartesian closed category and a linear category, which is an SMCC, and you have this adjunction that makes where both functors are monoidal. So you have a monoidal adjunction between them. Whereas in the pictures for the previous models, things are a little bit more complicated. You have to explain to people that, yes, you have a linear category and you have a comonad over it, which is the bang operator. And whenever you do that, you always have a collection of other adjunctions that starts with the Eilenberg-Mohr category, ends up in the co-Kleisli category. And as I was saying, you can invent nice packaging names for the comonad that you need. I'm kind of calling here linear exponential comonad, but lots of times I don't use the term exponential because it's confusing for logicians and stuff like that. And wait, because now we have all this, we have three type theories and three kind of notions of models. And are these models equivalent? How do I choose one? How do I choose the model morphisms? And what do we do with that? Because all these three models are sound and complete. And I say that the solution to this conundrum is using internal language theorems. And functional programmers might not like it so much because it's more work for them. They have to think harder. But, and now I'm kind of just using Miles' slides to explain these notions of internal languages and the notions of internal language theorems that I say we should go for. So given any calculus or kind of type theory TOR and a class of complete models for this given calculus, you can organize the models that you have into certain categories, but for that you have to find the suitable model morphisms. And this is not as trivial as people might think. You can organize theories of this calculus into a category called TH of the TOR. And again, you have to find suitable theory morphisms. And then, and that's the hard bit, you have to check the validity of the internal language theorem. So you have to show that the models of TOR as a category should be equivalent to the theories of TOR. And these are the guys that I say are the best models of, and I'm calling it here a calculus, but I could be calling it a type theory tool. And these things should be determined up to equivalences. So that's kind of a bit of work, right? You have to define this internal language out of the models, or the model categories that you have. You have to define a syntactic category out of the theory of the type theory. You have to invent this functors, and you need to show that for any model M, you have to have that the syntactic category of the internal language of M is equivalent to M. And for any theory T, you have to show the opposite sort of relation. And for simple type theories, you even get an isomorphism. But if you're kind of trying to be ambitious, then you have to do the same things. And for dependent type theories, it only works at the level of equivalence of categories. But the main thing is that the internal language theorems are the same. You kind of have the same notions of internal language and syntactic category, and the same sorts of adjunction-like laws. I mean, it is an adjunction, are satisfied. And then soundness and completeness, which kind of logicians tend to think as being enough for a good model, they are not enough, because when you're doing this categorically, you might end up with simply an internal language functor of the direction with the domain and codomain desired, a syntactic category functor, again, with the domain and codomain desired. But sometimes you only get a mnemonic natural transformation for a theory T. And as I was saying, this won't do. We won't get what we actually want. And in particular, that's what is happening here. When we do this sort of calculations for ILL, DILL, and NLL, we notice that we notice in this paper, Relating Categorical Semantics for Intuitionistic Linear Logic, that the internal home theorems kind of insist on more precise definitions of what we're doing. So the take-home kind of conclusion from this paper is the categorical models need to be more than seldom complete. They have to provide this internal language. And then we can talk about working on the category theory or working on the type theory and being able to obtain results that can be transferred without further problems. And then, if we kind of got that, we kind of can decide which kind of the kinds of monoidal adjunctions that we need for the lambda calculus that we think is the best one. But, to my mind at that stage, DILL was the best because it was less verbose than ILL and closer to what we wanted in terms of semantics, because it's closer to NLL, but not quite. NLL is too big. It has the easy formulation of the promotion rule. It contains this usual lambda calculus as a subsystem, which I thought was very important for the idea of linear function programming. But, lo and behold, if we're paying attention to our target audience, the functional programmers would prefer to use a variant of this calculus. They would prefer a variant where you have two function spaces, the function space that we know and love and the linear function space, and then forget about the modality. And that's why the title of the talk is Going Without. And that's cool. I'm all in favor of going for our target audience and doing what people want. But then we have a problem because the categorical models that we had before are not for this variant. And moreover, modeling this categorically is not a total triviality, because all the models that we discussed before have a notion of modality created by the adjunction. So all the adjunctions will create a functor, which is a comonad that, that corresponds to the bang operator. And now we don't want to have a bang operator because you want to have a very precise model of the system with the two kinds of implication. And, you know, then what it means is that if you are a category theorist working for your favorite function programmer and trying to produce the models for them, the one way I know of doing that is going for more serious mathematics and using fibrations or index categories. I cannot do it, at least at the moment, I cannot do it without this extra theory. And so this is the calculus that actually everyone wants to implement instead of the ones that I was discussing before. And as you can see, the only thing we have is the two different kinds of, the context is a dual context. You have linear and non-linear things, and you have linear and no linear implications or function spaces. And, you know, I'm going very quickly here because I'm actually just trying to sell ideas, but you can look at the paper in applied categorical structures to see all the details. And this, so the whole idea here goes back to Liouville's hyperdoctrines, which is something that Maietti is an expert. And we modify the setting of the hyperdoctrines to capture the separation between intuitionistic and linear variables. So we have this base category B, which models the intuitionistic context. And over each context gamma with no linear variables, we have a category that is a model of linear logic. So the fibers are now symmetric monodal closed categories with finite products, and they model the linear constructions. And we have this, this traditional, by now traditional picture where we do substitution. The main thing is doing substitution via the pullback functor. And you know, it's a generic, what we have is this generic way of combining traditional intuitionistic logic with linear stuff using using this notion of index category. And for those guys, we can have our internal language theorems proved, and you can just check them. What I think is missing for us, and what the reason again why I wanted to talk about that, is a further understanding of how much more we can do. And I'll kind of going to come to that. So, you know, in particular, I wanted to know if we can do the same for different kind of, I mean, we can do that for modal logic S4, and this is something that that we did later. But what about the other modal logics? That's kind of, I mean, all the newer modalities that people in Denmark are producing, they're all S4. But the logicians don't particularly, I mean, they like S4 as much as any other modal logics, but there's lots of others that we should be doing. Another interesting one is, can we do the same for relevant logic? Can we kind of not only, I mean, we can model S4, you can model relevance logic, but can we do the same trick of forgetting about the modality? Kind of, can we do the same calculations to make the modalities disappear? And I hope so, but I have not managed to do any of these calculations yet. And I think I wanted to conclude earlier. Well, it's not so much earlier, but I wanted to conclude earlier that that linear type theories are interesting both from the implementation and from the theory perspectives. And the theory kind of, the theory has two sides to it actually, right? Because there's the type theory side, and that's the logic that comes in when you forget the terms. And I kind of wanted to recall this old idea that soundness and completeness are not enough, that we need to have the internal language theorems. I think, you know, people are not paying enough attention to the morphisms that we actually have to carry with us when we're doing categorical work. And I think paying attention to the implementers is really very necessary. And as far as I can tell from the two videos on YouTube about linear Haskell, the implementers are kind of, as I say, using this calculus that is slightly different from the ones that we actually had proved results for. So, you know, lucky for them that we had done this work before. And kind of finding the right abstractions depends on checking lots of other systems. So I think we need more experimentation. And I hope to convince some of you to actually take this challenge of doing the calculations thoroughly and through and to the end. So I think it's definitely a good time to sharpen our theoretical tools. And with that, I think I'm going to stop and try to have more of a conversation than a monologue. Thank you.